शो हो रही है पीपीटी वाली? जी सर
जी सर,
बिल्कुल।
अब सर लाइव हो गए सर आप।
चलें, ठीक है। ठीक।
जी सर, वो अपना लाइव है और ऑडियंस ना ज्वाइन कर रही है, तो आप स्टार्ट कर सकते हैं सर सेशन।
चलें, ठीक है। अच्छा, मेरी स्क्रीन शो हो रही है? जस्ट प्रेजेंटेशन शो हो रही है ना?
जी जी सर, हो रही है प्रेजेंटेशन शो सर आपकी।
चलें चलें, ठीक। Just- चलें, ठीक है।
जी सर, आप कर दें स्टार्ट।
कर दूं स्टार्ट? चलें।
जी सर।
Good evening, everyone. My name is Dr. Iftikhar Ali. I am from Department of Agronomy at University of Agriculture, Faisalabad. It's my great honor to give a brief introduction about research and developments on smart farming. From the previous few years, we are working in a close collaboration with Nanjing Agriculture University, and we are working on construction and application of smart farming technology to be used in Pakistan. So let's start with our presentation. Uh, why do we need smart farming? Basically, it's because of the urgent demand for food security. You know, our food security faces challenges like rapid growth in population, limited arable land, increasing shortage of water resources, and frequent extreme climate events, and most important, tension in international markets. So, to overcome these challenges for food security, we must increase the efficiency of our crop production practices in the field. Uh, if we talk about smart agriculture represents the highest level of agriculture development. There are four types of terminology coexist with various focuses. If we talk about information agriculture, it focuses on collecting data, collecting information about agriculture practices. And if we talk about digital agriculture, it focuses on digitalization and modeling of the collected data. And if we talk about precision agriculture, it is related to farm operations, precise farm operations. But our smart agriculture, it But smart agriculture integrates all three components together so that agriculture operations should be guided by a brain and the brain should be supported by data. So we need sensors to collect digital data, run models to extract information and make decisions, and then guide machines to operate precisely. Only in this way we could maximize the resource use efficiency as well yield of crop. Now I will present the technical framework of smart farming technology. Smart farming technology is a combination of crop science, remote sensing, computing science, and agriculture engineering. If we divide it into main components, we will have three main components of smart agriculture. One is quantitative remote sensing, other is system modeling, and yes, third is equipment innovation. So remote sensing is eye of this smart farming technology. And the crop modeling is actually the brain of this technology. And the third one Equipment innovation, precision agriculture is actually the hands of this technology. So these three together work and make smart farming technology. So right now, I will show you some recent work in smart farming technology from these three aspects. First is crop sensing and agriculture conditioning monitoring. Second is crop system simulation and prescription design. And third is intelligent equipment and precision operation. To address the issues in accuracy, timeliness, and scale integration, the acquisition of multi-source cropping data at different spatial scales, followed by the analysis of characteristics and features for data interpretation and feature extraction, and the construction statistical and machine learning are radiative transfer models for crop trait estimation, and then end up with the generation of thematic products such as crop type maps, growth indicator maps, disease and disaster damage maps, and yield or grain quality maps. Due to limited time, I will only show a couple of cases on this topic. So, first topic is our will focus on remote sensing, collecting data through remote sensing devices. So I will present some devices. First is portable canopy devices. We have to develop uh, portable canopy devices which can collect the data in the field directly. In vegetation remote sensing domain, the most commonly used approach is spectral vegetation index. To obtain spectral vegetation indices, expensive spectral sensors are needed. We have to extend spectral sensing techniques from expensive laboratory research to affordable and practical products. Here is an example of portable device which has a two-band sensor with one red band and one near NIR band. Model CGM302 works in a passive manner, that is using solar radiation as the light source, while the model CGMD402 works in active model. It has a built-in light source beside the sensor, which means it can work in all light conditions. It is competitive to counterpart commercial products. The device saves reflectance and vegetation index readings, and it is easy to use and for local extension specialists and professional farmers. In addition to handheld mode, the sensor can also be mounted on drones and tractors to collect spatial distributed data efficiently and can also be installed in the field as an Internet of Things node to collect temporarily continuous data in the field. Sensor only costs several $100s to fabricate, which is much cheaper than commercial products. To date, a large number of studies have been conducted to determine the optimal bands, vegetation indices, and predictive models for crop traits monitoring. MERIS, terrestrial chlorophyll index, is a commonly used vegetation index for leaf chlorophyll content estimation. Actually, this leaf chlorophyll content is strongly linked with leaf nitrogen content and photosynthesis capacity of plants. A major problem with canopy sensing in a known imaging sensor at early stages of crop growth is the background effect. That is, we want to get vegetation signals, but what non-imaging sensor obtain is always a mixture of vegetation signals and soil signals. So we don't want soil signals. We just want only canopy signals from plants. So we have to collect data during off noon observing hours can reduce contribution of sunlight soil to canopy reflectance. Constructed a new vegetation index like LICI for improved estimation of leaf chlorophyll content. Another instrument, we can use drones and we can integrate textural and spectral information together, and we can monitor biomass and yield of crops instantly. So we can combine these two indices and we can improve the prediction of above ground biomass. Another challenge is field boundaries delineation. We need to collect high spectral images, and let's suppose we have developed a sample-free framework for crop field boundary delineation by integrating super resolution image reconstruction and dual image corrected segment anything model. This model can be applied for field scale precision management of pesticide or fertilizer prescriptions. Application of this model uh, is visible in this slide. You can see we have applied Kenya, Pakistan, and Argentine field, and we can get resolution of 1 meter, and we can see the small fields using this model. You these technology to apply these technologies in Pakistan from previous 2 years, we are collecting data from Punjab. You can see this is our study area. We are collecting rice data from three pockets of rice. We are collecting leaf area index, above ground biomass, harvest index, and grain yield. Here are some pictorial views of our data collection campaign last year. We have collected leaf area index from adjointing stage, booting stage, and heading stage, and then at maturity from different districts like Gujarat, Gujranwala, Lahore, Sahiwal, and Faisalabad. Then we have also collected data about above ground biomass and then finally yield from these different districts. Then we have developed maps for acreage. Then we have developed for maps for leaf area index, then leaf nitrogen, and then above ground biomass, and then yield for rice in different districts of Punjab. If we summarize this one component, that is remote sensing, we have to develop solutions to collect crop growth information on the ground with low cost portable and IoT sensors. Then we will move to drones, in the air with drones, and in the space with multi-source satellite. Basically, they provide information at different scales. Portable and IoT sensors focus on field level, drones and IoT network focus on farm level, and satellites focus on the regional level. We aim to establish a ground airspace integrated technology platform for crop growth monitoring to address three types of questions. Where are crops growing? How are crops growing? And what's the production of these crops? So using this component, developing this component, we will be able to get the information about crops on a regional scale that where are and which crops are growing and what is their production and we can monitor their status in real time. Second component of this smart farming technology is crop system simulation and prescription design. This topic will be very well covered by the Professor Aftab Wajid because he is crop modeling expert. Uh, as I said earlier that this smart farming technology has three components. One is crop sensing, second is crop modeling, and third is precision agriculture and innovative equipment. First, I said this is eye of this system. Second, crop system is the brain of this technology. So in this crop system simulation, we collect data and we construct models of growth, knowledge model, regulation model, and profit model. Then we develop prescription designs for sowing, transplantation, planting density, fertilizer, and water use. And then we diagnose our crop, real-time monitoring and intelligent diagnosis and precision regulation And then we predict growth prediction, crop development, photosynthesis, yield, and quality. And then we can also study the impact of these practices. We can also study the impact of climate change. We can also find the impact of genotype and land cover and other management practices using this crop system simulation. Then application platform for cropping system design. We can develop desktop, web page, and application versions of these crop system simulation models. We can we can apply it for cropping system design technology. Here I am giving one example. If we integrate Epsom model with R and we give them phenological and yield attributes, and we also give elevation model and some other parameters, we can predict yield, spatial yield, and heterogeneity of simulated yield under zero application of nitrogen in B. 100 kg nitrogen per hectare if we apply, we can predict yield of wheat at large scale. And if we apply 200 kilogram nitrogen, what will be the effect of this nitrogen application over large field of wheat? This is an example in Egypt. The third component, as I said, third component is precision operation of farmland management. These are the hands of smart farming technology. We collect data from crop sensing, then we develop cropping system through crop modeling, and then we apply this knowledge and we innovate, we develop new machinery. The third part is precision operation for farmland management. The goal is to build intelligent equipment and precision operation system which integrate the functions of information acquisition, variation analysis, prescription generation, and variable rate application from soil preparation to harvesting procedures. This precision operation technical framework covers cultivation practices, planting practices, management such as spraying, fertilization, irrigation, and finally harvesting. So we have to develop new machinery for each operation so that we can intelligently control these farm operations. For example, here is a new equipment unit for monitoring wheat sowing status and a precision and variable rate field operation system based on management, prescription, and navigation system. You can see an unmanned tractor is running in the field and performing the sowing of wheat in the field. So we have to develop this machinery and connect it with our previous data collection, that is crop sensing and then system modeling, and we can combine it with our equipment and we can perform precise sowing. Here is an example tractor-based crop growth monitoring and analysis on the go. This is a variable rate fertilizer tractor which integrates canopy sensor for crop growth monitoring and analysis on the go. Irrigation is an important operation in rice management. Here I am showing a low-cost pooling type soil moisture sensor, which can be integrated with a canopy sensors to collect the real-time moisture information of the crop soil. The sensor node is connected into the IoT for continuous moisture monitoring and smarter irrigation decision making. Here you can see an unmanned weed sowing is happening. Tractor is going straight, sowing the wheat, and then in the second you can see it is taking U-turn and performing the sowing of wheat. Third, you can see a combine harvester is harvesting the wheat crop. It's an unmanned tractor and combine harvester. And in the fourth, you can see it's taking U-turn. So, by integrating technological innovations in wheat growth monitoring, prescription generation, and precision operation, the unmanned farming operation is being performed, supported by a navigation system. The development of this technology is mainly motivated by the lack of sophisticated tractor drivers and the inadequate, insufficient quality of operation. Actually, why we need these type of technology? Why we need driverless tractor and driverless harvesting? Because right now, we don't have sophisticated tractor drivers, inadequate, insufficient quality of operation. So if we develop such kind of technology and they do their work precisely as I am showing in these videos. This is smart farming. So uh, after uh, developing this technology, we have to demonstrate this technology to the farmers. From laboratory research to field practices, there are still a lot of integration and customization to be done. The core technologies for demonstrative applications include precision design of cultivation schemes, quantitative diagnosis of growth indicators, dynamic prediction of crop yield and quality, and variable rate operation for production management. They are supported by management of basic data, parameter databases for model operations, and new technology services more. Here are some glimpses of our last year activities. We organize field demonstration day events every year during sowing and grain filling stages with extension stations. Participants are work farmers, news media, and cooperative and some extension experts. With local farmers and extension agencies, we have to demonstrate platform system, thematic maps, and portable devices. These events are useful for promoting the awareness of using new technology in crop production and foster the upgrading of agriculture industry. Here I will show last year we monitor rice yield on the field and we validated our system. The yield data for the single point and the 50-meter buffer was estimated as 4.68 and 4.75 ton per hectare respectively. So, what are the prospects in smart farming technology? I want to talk a little about the prospects of smart farming. As you know, the construction of smart farm or unmanned farm has started and speeding up across globe. It is a response to the critical questions of who is going to plant crops and how to plant crops in the new era. The operations of these farms need deep integration of information, agronomic, and agriculture mechanization technology. Our farm should be look like this in the future. Here you can, on the left side, you can see a lot of drones working together and spraying in a large field. On the right side, you can see unmanned driving of multiple intelligent machines. So this is the future. We have to decide who will do the farm operations in the future. What are take-home messages? Here I want to summarize six key points to develop smart farming technology. These are necessary from different procedures, such as a system of monitoring network, a suite of prescription maps, a chain of precision operations, based data management platform, a basic database, and a mode of one-step service. So we have to work on these 6 points if we want to develop an effective smart farming technology. We are using advanced information technologies to make the transition from traditional agriculture to modern agriculture. We hope crop production could be more efficient and easier. As we have seen today, this is possible with the use of smart farming technology. With that said, I would like to conclude my presentation. Thank you so much for your attention.
सर
जी,
अशाद साहब जो हैं वो अभी लेट हैं तो उनका सेशन फिर हम बाद में कर लेंगे। तो कुछ स्टूडेंट्स के क्वेश्चंस हैं।
हाँ जी, हाँ
एक
जी।
स्टूडेंट एक स्टूडेंट ये पूछ रहा है कि स्मार्ट फार्मिंग का कमर्शियल फार्म्स को बहुत ज़्यादा बेनिफिट है, तो जो छोटे स्केल के फार्मर्स हैं वो इन 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 फैसिलिटीज़ को कैसे अवेल कर सकते हैं?
अच्छा, अच्छा। पॉइंट ये है कि ये स्मार्ट फार्मिंग टेक्नोलॉजी अभी डेवलपमेंटल स्टेजेस पे है। तो हम कोऑपरेटिव फार्मिंग को ले सकते हैं। जब हम एक सर्विस सेंटर एक बनाएंगे जो कि स्मार्ट फार्मिंग टेक्नोलॉजी प्रोवाइड कर रहा होगा, तो फिर वो एक एरिया में एक एरिया में जितने भी फार्मर्स होंगे उनको कंबाइंड सर्विसेज प्रोवाइड करेगा। तो इस तरह हम एक से जो स्मॉल स्केल फार्मर्स हैं उनको भी इंक्लूड कर सकते हैं और हम कंबाइंड सर्विसेज प्रोवाइड करेंगे फ्रॉम सोइंग टू हार्वेस्टिंग।
सर जैसा कि देखा जा सकता है कि कॉर्पोरेट फार्मिंग का जो जो ट्रेंड है वो स्पेशली हमारी लोकल टर्म्स को देखते हुए वो इतना ज़्यादा कारगर नहीं है। तो सर इस हर्डल को हम किस तरह टैकल करेंगे कि हम अपने लोकल फार्मर्स को कॉर्पोरेट फार्मिंग की तरफ लेके आए?
हमें बस हमें सारी टेक्नोलॉजी डेवलप करने के लिए हमें बहुत ज्यादा काम करना पड़ेगा। जहाँ जिन कंट्री जो इस पे काम कर रही हैं वो ऑलरेडी उन्होंने ये सारी टेक्नोलॉजीज डेवलप कर ली हैं और सालों से वो लगे हुए हैं और वो अब फील्ड में है। तो उन्होंने फार्मर्स का ट्रस्ट गेन कर लिया हुआ है और उनकी जो टेक्नोलॉजीज हैं वो अब फार्मर्स उसको एक्सेप्ट कर रहे हैं। इसलिए अभी टाइम लगेगा। अगर ओवर द ईयर हमें ये सारी टेक्नोलॉजी एक लार्ज स्केल पे डेवलप करके फार्मर्स के पास जाना चाहिए। तब हम उन फार्मर्स को इस न्यू ट्रेंड्स न्यू फार्मिंग टेक्नोलॉजीज की तरफ लेके जा सकते
जी सर, बहुत ज़्यादा शुक्रिया आपका। अशाद साहब को अभी थोड़ा टाइम है तो अभी हम फिर सेशन को एंड कर देते हैं सर।
हैं। चलिए ठीक।
चलें जी सर, बहुत शुक्रिया। थैंक्स फॉर योर टाइम।
चलिए ठीक। ओके।
ओके।
ओके। अल्लाह हाफ़िज़। ओके, अल्लाह हाफ़िज़। थैंक यू सो मच।
जी सर, वेलकम।